Vitalii.
Thanks for the introduction. My name is Vitalii Emelianov. I'm a PhD student in RIA, and I'm going to present our work on fair selection in the presence of implicit variance. And this is a joint work with Nicolas, Gast, Krishna, Gummadi, and Loiseau. So, many selection problems such as hiring or admission are affected by discrimination, where the outcomes for certain individuals is negatively correlated with their demographic attributes. For example, recently it was found that since 1990, Black applicants received 36% less callbacks compared to white applicants with identical CVs. The similar issue happened with one of the top-ranked university in the US, where the white applicants prefer to Asian applicants. Employers also tend to discriminate by gender and age. To mitigate the effect of discrimination, several fairness mechanisms were proposed. So the first one is Rooney Rule, which requires that at least one candidate from the underrepresented group should be invited for an interview. And it was first introduced for hiring football coaches, but now it's used in many different businesses. Another popular hiring rule is 80% rule, which requires that the selection rate for the underrepresented group should be at least 80% of that for the overrepresented group. And it's also widely used for hiring. A stricter version of 80% rule is demographic parity, which requires that selection rate should be equal across the group. And this is one of the most standard definitions of fairness in algorithm decision making. Fairness mechanisms are frequently debated. On one hand, they promote the inclusion of deserving candidates from the underrepresented group. But on the other hand, while accepting someone from the underrepresented group, decision maker rejects someone from the overrepresented group, and it can decrease the total quality of selection. And in fact, most scientific literature show that there is also kind of trade-off between the fairness and quality of selection. Worth to note that in most of this literature, real source of discrimination is almost never studied. So might be that it's important to take this source of discrimination into consideration, and we can get deeper insights about fairness in selection problems. So one of the most common explanation for discrimination is implicit bias phenomenon, where some applicants, some group of applicants have unconsciously negative perception by the decision maker. So the mathematical analysis of selection with implicit bias was initiated by Kleinberg and Raghavan, and they model it as follows. They suppose that each candidate has a real quality W, which is hidden from the decision maker, and what he observes is only the estimate of quality, which I denote by W hat. And for the group A, the estimate is equal to quality divided by some beta, which is a bias parameter. And the larger the bias parameter, the more biased the decision maker against the group A. And for the group B, the estimates of quality are unbiased. Let's note that the quality distribution follows quality distribution is group independent. So it will be important for the further discussion. In their paper, Kleinberg and Raghavan show that Rooney rule actually improves the selection quality under the presence of implicit bias. And this is a bit controversial with the conventional wisdom that fairness harms the quality of selection. In our work, we argue that even in the absence of implicit bias, decision maker can have different level of experience while evaluating candidates from particular groups. So the precision of signal will be different and will depend on the group value. Also, it could be that candidates from different groups could have different variability of performance. For example, it was shown that male tend to have larger variability while performing standardized tests compared to female. And we call this as implicit variance phenomenon because the presence of different variability across the groups is not known to the decision maker, or it's not controlled. So we model it as follows. As with implicit bias model, each candidate has some quality W, which is group independent, but decision maker observes only the estimate of quality. And for group A, it's quality plus some zero mean noise with variance of estimation equal to sigma A. And for the group B, it's W plus zero mean noise with variance of estimation sigma B. In this work, we ask the question, so what will be the effect of fairness mechanisms on the quality of selection in the presence of implicit variance phenomenon? We model the selection problem as follows. We assume that there are n candidates which come from two group A and B. Decision maker observes only the estimate of quality W hat, and he selects some fraction alpha out of total number of candidates. While doing so, he selects at some rate from group A and at some rate from group B. When he made his selection, he observes the real qualities W, and the utility of selection is measured as the sum of qualities of selected candidates. So the most natural algorithm that decision maker can use is to be group oblivious, which means that to ignore the group information and use only the estimates as the decision factors and keep best alpha according to the estimates. On figure below, we show the distribution of quality as well as the distribution of estimations. In our theoretical evaluation, we assume that quality follows normal law, and we assume that the variability of estimation for group A is larger than for the group B. And we see from this graph that when the selection is made such that less than half of population is selected, then group oblivious will tend to underrepresentation of low variance group B. To mitigate the effect of discrimination, decision maker can use some group fair algorithm. And in our work, we study a generalization of 80% rule, which we call gamma fair algorithm. So basically, in this case, decision maker selects best candidate from each group according to the estimate of quality, but he maintains the following condition. Roughly speaking, he ensures that selection sizes does not differ too much across the groups. And how much they differ is controlled by the parameter gamma. The gamma fair algorithm has two important some cases. First one is when gamma is equal to 0.8, and it corresponds to 80% rule I described before. For gamma equal to 1, it reduces to demographic parity. Our main result is as follows. We proved that for any value of budget alpha, demographic parity strictly improves the utility of selection compared to group oblivious algorithm, and gamma fair algorithm for gamma smaller than 1 weakly improves the selection quality compared to group oblivious algorithm. And to understand its result, let's look at selections made by different algorithms. So on first graph, we show selection made by group oblivious algorithm. And as we remember, using group oblivious algorithm leads to underrepresentation of low variance group. On middle panel, we show selection made by demographic parity, and we remember that demographic parity ensures that selection rates are equal across the groups. And now, to be able to compare these two algorithms in terms of utility, we should know what will be the optimal decision in this setup. And we study Bayesian optimal algorithm, which is such decision maker who does not know the real qualities, but he knows the distribution of quality given the estimates. So actually, perhaps surprisingly, the Bayesian optimal algorithm will lead to underrepresentation of large variance group. And to understand this, let's imagine the following situation. So Bayesian optimal algorithm is faced with two options. First is candidate from group A, and the second is candidate from group B. And the estimates of quality are exactly the same for both candidates. And decision maker knows that this candidate is from low variance group and this candidate is from large variance group. Then he will definitely prefer the candidate from low variance group because he will be more sure that the estimate of quality will not be that far from the real quality. So we see that demographic parity makes closer decisions in terms of selection compared to group oblivious algorithm. And this concludes the proof. So to summarize, we prove that in the presence of implicit variance, group oblivious algorithm leads to underrepresentation, and we can use group fair algorithm to reduce underrepresentation, to reduce the effect of discrimination, and at the same time, it will lead to better quality of selection. We also extend this result to two-stage setting. So as before, there are n candidates, and we observe some estimate of utility for this candidate. We select some fraction alpha 1 out of them, and the real qualities became observed. After the decision maker refines its selection to meet the new selection budget alpha 2. So this two-stage setting can model typical hiring pipeline when at first stage some low precision estimate is given. For example, it could be a CV of the candidate, and at the second time, the quality is observed more precisely, and it can correspond to the interview stage, for example. So if we look only at the one-stage decision making, we remember that group fair decision making made better selection compared to group oblivious decision making. And on this graph, we plot the difference between utility by demographic parity and group oblivious algorithms for the one-stage case. And we see that for every value of alpha 1, this difference is positive, which basically illustrates the results of the previous theorem. Now let's look at utilities corresponding to two-stage selection. And again, we compare utility of demographic parity and group oblivious algorithms. We fix alpha 2 to 0.1, and we vary the value of alpha 1 from 0.1 to 1. So there are two important subcases. First, when alpha 1 is equal to alpha 2 or very close, then it means that every selection is made at first stage. So the two-stage pipeline reduces to one stage, and we remember that in this case, demographic parity was strictly better compared to group oblivious algorithm. So that's why we see that this difference is positive here. Other cases when alpha 1 is 1 or close than 1, then every candidate is selected at first stage, which means that all selection is made at the second stage where the real qualities are known. So since the qualities come from the group independent distribution, then there will be no difference between demographic parity and group oblivious algorithm in this region. Overall, we can prove the following result. When alpha 1 is close to alpha 2 or alpha 1 is large, then demographic parity strictly improve the selection utility compared to group oblivious algorithm, and gamma fair algorithm for gamma smaller than 1 weakly improves it. In our modeling, we assume that in our theoretical evaluation, we assume that qualities follow normal law, but we can imagine some application when it's not true. For example, if we want to hire researchers, we might use the citation count as a proxy to their quality. And we remember that citation count can be modeled as Pareto law. We do a numerical experience in this case as well. And we plot the difference between demographic parity and group oblivious utilities. And we see that in most of the cases, demographic parity strictly improves the group oblivious algorithm, the utility compared to group oblivious algorithm, except for one region when demographic parity harms the selection, but the harm is relatively small. Also, we do numerical simulation with other distributions, for example, uniform, and some experiments on real data, which can be found in our paper. To summarize, in this work, we propose a model of implicit variance. We assume that even in the absence of implicit bias, decision maker can have different experience while evaluating candidates from different groups. That's why the estimate of quality can have different variability. We show that in this case, group fair decision making is beneficial to selection quality, and it also mitigates the effects of discrimination. Finally, we can extend our modeling in two directions. First, in our modeling, where we assumed only the presence of implicit variance, but we can assume that both implicit bias and implicit variance are present, and our model can be extended in this direction as well. In our modeling, we assume that the quality distribution is group independent, but we can imagine that it can depend on the group as well, and it can be added to our model easily as well. So that's it. Thank you for your attention. And if you have any questions, please, I will be happy to answer them.